All right, today we're going to talk about potential energy diagrams. So yesterday we reviewed some of the calculations. We went through all of some of the terminology, hit the highlights of the reading that you were supposed to do. Again, be ready for a quiz this Thursday. And we'll cover those calculations. Be prepared to see a problem like we did yesterday where we kind of walked through all the different pieces, whether it was a temperature change versus a phase change. Again, you'll only have those with water, so you need to make sure that you know the important temperatures of water. What are they again? Think to yourself. 100 degrees Celsius and 0 degrees Celsius. You've got to know those. All right, so that's going to be part of your quiz on Thursday. The other part is going to be on the terminology, what you're supposed to read, so make sure you know all those because they're going to be random questions of the reading that you were supposed to do. Today, as I said, already, you guys are going to learn about potential energy diagrams, and that's what I have right here. You guys should have a sheet in front of you. You're going to want to take the same notes down that I take. I guarantee you that you will see one of these on your final exam. Every single year, they love to put the graphs. You're going to see these. You're going to see heating and cooling curves, phase diagrams, any type of diagram they love to put on there because they assume that anybody can do those questions because it's just interpretation. All right, so we're going to talk about these two. So we can see, obviously, that there are two different yet similar graphs that we're looking at here. Okay, so I'm going to zoom in a little bit. Okay, you got the top one and the bottom one, which I believe are in the same order that what you guys have on your sheet. Now, if you think back to last week with the video that you watched, okay, they kind of started talking about them, so you may remember some of the different pieces. But we're going to go through and make sure we get all the notes on them and make sure you guys truly understand kind of what's going on with those because you will have to be able to interpret the different pieces of those. Excuse me. So, if you take a look, you can see that they all have, they both have these hills in the middle, and then there's lines at the beginning and the end. And over here, again, potential energy diagram. All right, they're dealing with the potential energy, the energy that's involved in a system, all right, within the reaction mechanism. So this whole thing, you know, it says time down here on the bottom, okay? As you go from left to right, it's really talking about the reaction pathway. All right, the reaction pathway. And that's going to be the same for both of those. Now, if we take a look, and if I was there in person and asked this, well, which one do you think is which? There's two types that we could have, exothermic and endothermic. So think to yourself, what does exo mean? All right, it means to release. Endothermic means to then, obviously the opposite, it means to absorb, to take in that energy. Okay, so which one's which? Well, how we understand and how we look at those is look and see where you start. So here we're starting at, on the bottom graph, we're starting at 10, and we're finishing at, well, if we draw these lines all the way across, okay, we can kind of see it. Oops, I didn't mean to erase there. All right, and then up here at the top, these are the kind of the three big lines that we're looking at. You can see that there's dotted lines on some of those. All right, there to kind of help you see where you're at. So each of those has three lines. So we want to see, okay, where does the reaction begin and where does it end up? All right, so if we look at the top reaction, it starts at 45 kilojoules and it ends up at 10. Well, what's happening? It's going from higher to lower energy. So what's it doing? It's losing energy, absolutely. So what type of reaction would the top one be? If it's losing energy, exothermic. Okay, it's an exothermic graph. If that one is exothermic because it's losing energy, we'll take a look here at the bottom. I'm going to switch colors. All right, we start at 10 kilojoules and we end up at 45. So we're taking in energy after we go through the entire process. So if we end up with more energy than we started with, obviously that's going to have to be endothermic. All right. So that's kind of the overall piece that you're looking at, identifying whether you have an exothermic or an endothermic graph. Now we're going to look and analyze the pieces that are within the graph. And I'm going to change colors here again just to make it a little bit easier to see. Okay, so first thing we're going to look at, if this is the reaction pathway, what do we always start with? any reaction, what's the pieces that we start with? This is review. You guys should know this. We've been talking about this for a while now. Those pieces, like I'm hoping that you're thinking about. All right, those are your reactants. Okay, your reactants. And then what do you end up with? Obviously, they're going to be called the products. And that's going to be true no matter which type it is. So I'm going to fill in both of those at the same time. Reactants, and we have our products. Whether you write them at the line or whatever, it doesn't matter. Just know that the reactants come first and the products come second. And that should be easy for us. Okay, so if this is showing the energy, the energy amounts that the reaction or the system has throughout the entire reaction pathway. All right, we can see. Okay, so we start out up here at the top with exothermic 45 kilojoules. Well, in order to get the reaction to go, it needs a lot of energy that you have to put in here. Okay, this is what we call our activation energy. We can have those reactants all we want. They can be right around each other. It doesn't matter. Okay, it doesn't matter. We can have those together, but we need something to get them going. And that's known as our activation energy. All right, the activation energy. It's also symbolized like this, as E sub A. Sometimes you might see it under the hill. All right, or it could be over there to the left. Doesn't matter. It's really going from where your reactants start to the top of that hill. That's your activation, no matter where it is. Whether it's underneath the hill, like I have with EA here, or if it's over here at the beginning with your activation energy labeled there. Okay. Now, that's how much energy it takes for the reaction to go, to activate it. Once you get up to the top of that hill, the rest of the reaction will just take care of itself. So you need a kickstart. All right, kind of like if you think about it, a roller coaster. All right, roller coaster, you got to go up that first hill. Once you get to the top of the first hill, all right, depending on the type of coaster you have, you're just going to coast the rest of the way. All right, or maybe if you've ever been to Cedar Point, the dragster that they have there, you kind of start off flat, and then you get shot 127 miles per hour straight ahead. You go up over this gigantic hill, and you come back down. The whole ride takes like 17 seconds. There's no way I would ever go on that because I'm too much of a chicken. But same idea. You have to have that energy that's there in those magnets to shoot the car fast enough to get over the hill. And that's exactly what the activation energy is doing. It's the energy that you've got to put into the system to get it up close to where it can go, and then all of a sudden it's just going to go down the rest of the pathway by itself. All right, and it's going to produce your products. Okay. Now, at the top of this peak, right here, you may remember this from the video, all right, right at the tip of that peak, all right, that's something that we've got to know as well. All right, so right here, this spot, this is called our activated complex. All right, it's the highest energy point of the entire system. When you get to that point, that's when the reaction starts to then, you're breaking your bonds and then you're starting to produce them to get to your products, or vice versa. Okay, whether you're either breaking the bonds to make new stuff or you are just forming them. All right, it's the highest, it's where you have the most amount of energy in the entire system. Okay, all right, after that, it's downhill from there. Then we can go down here to our products. Now, what we're interested in, if you think back to yesterday with the reaction mechanisms that we talked about, what formed in between? All right, what formed in between? Those were the intermediates. All right, so where you might find those intermediates is in, I'm going to shade it in blue here. All right, this whole area, this hill, this is where you would find your intermediates, if you have any. Okay, you're going to find them in that middle part of the reaction. And then obviously they're gone, like we said, to be an intermediate. They're formed and then they're consumed. By the time you get back to your products, they are gone already. So that would be the most likely area in terms of energy where you would find those. You got a lot of energy, lots of things being formed and being consumed. The piece that we're also interested in, though, is this right here. The difference between the reactants and the products. So where this arrow is right here, okay, this is what we call delta H. And that's exactly what we were talking about yesterday. What is delta H? That's your heat of reaction. That's your enthalpy. Okay, that's your enthalpy piece. All right, so the change in heat, that's your heat of reaction. It's between the amount that you started with the reactants and the product. So for here, our delta H, all right, is going to be that final minus initial. So we have 10 kilojoules minus 45 kilojoules. All right, so our delta H for this top one is going to be negative 35 kilojoules. Does that make sense with what type of reaction we have here? Why? Why does that make sense? This is a question you've got to be able to answer. Why does that make sense? Well, a negative delta H means we have an exothermic reaction. If it was positive, we would know that we've done something wrong. Exothermic, they release that energy, they release that heat. So then we, excuse me, then we've got to have a negative delta H in the end. Your products have to be lower than the reactants, so you're losing energy in that system for it to be exothermic. If we jump down here to the bottom, all right, now if you have more questions about it, write them down, save them. All right, we will, when I come back tomorrow, we can kind of shore up any details that you may be confused about. All right, but let's go down and take a look at endothermic. All right, I want you to actually pause the video here.